Siglent of North America has lent me this SDG7102A function generator to evaluate for the past 3 weeks. It has some very good points, and it has some issues. It is a beta unit, and as far as I know, it's the only model like this in North America currently. They've placed no restrictions on what I can say in the video. They will not review anything I'm saying before I could give it to you. And they have given me permission to take the cover off and show you the inside. So I hope you enjoy the clips that are coming up. And in the end, I will have a brief discussion of what I found. And if you do like this video, please click like and subscribe to me too. Thank you very much. The SDG7102A demo unit I was sent is a fully optioned model with the crystal oven and IQ modulation options for a total list price of $22.6 thousand. So here we're going to look at the difference between the square wave and the pulse mode. So currently we're in pulse mode, and I'm at the maximum frequency of 312.5 megahertz, and you can see the waveform here, and this is with the 500 picosecond rise and fall times. At this frequency, the maximum output swing is 3 volts peak to peak into 50 ohms. And I'm getting rise and fall times on the order of 600 or 700 picoseconds, it says, but it's faster than that because we're near because of the limitations of the oscilloscope. So let's see what happens when I change to a square wave. Now the frequency is dropped to 240 megahertz because that's the highest frequency that the generator will do in square wave mode. Let me start. And you can see here now that the, let me start and stop this so we get new measurements. We're getting rise and fall times of about a nanosecond. Now let's go back to the pulse mode. And now we're back to the 600 and some picoseconds. So let me go to this mode here. Now let's go back to square wave mode. So you can see at the 240 megahertz, the square wave really does not look much like a square wave. The pulse mode's a bit better because it has the faster rise and fall time. So let's go to 200 megahertz. Okay, so here we are in pulse mode. Let's go back to square wave mode. Now we're at 100 megahertz. This is square wave mode. This is pulse mode. Okay, so if you look now, I have the output of the generator set in pulse mode. I have both the falling edge and the rising edge set at 500 picoseconds, 25 megahertz frequency, 50% duty cycle, and 12 volts peak to peak. If you look at the scope, we're getting about 11.4 volts amplitude, not the 12 volts we set. So again, we have the amplitude error. And the rise and fall time are on the order of 2 nanoseconds for 12 volts. So let's see what happens as we change the amplitude. We come down to 10. The rise and fall times are now about 1.7 nanoseconds. So it seems to be slew rate limited. Now we're at 6 volts. And again, it scales, so it should be 6 volts peak to peak, but as you can see from the cursor lines, it's 5.7. But now the rise and fall times are down to 1.2 nanoseconds. Let's go down some more. When we go to 3 volts, you'll hear the relays click, and it changes into some sort of different output mode. You heard it click. Now, let's look. So now our rise and fall times are on the order of 500 picoseconds. So this is close enough now to the rise and fall time of the scope. The scope may actually be limiting it. So, so anything faster than this, take this with a grain of salt. Let's go here. This isn't really speeding up. Let's drop down. Let's go down to half a volt and speed this up. And we're staying right around 600 picoseconds. So it says 600 picoseconds, but it could be as low as 300 or 400 picoseconds. Again, because we're running at this speed, we're running into the rise and fall time of the scope. So it's fast, but not fast throughout the whole range. So let's go back up. Let's come back up here. Half a volt. Let's go back up and okay, 2. Yeah, there's a relay click between 1 and 2. So there's some other mode it goes into there. 3 volts. And we're on the order of 500 picoseconds here. 6 volts, it's slowed way down. So it goes into some different modes. So it's fastest for 3 volts peak to peak or less. So now I want to look at the output amplitude accuracy of the SDG7102A. And so right now, let me run it into both my Tektronix oscilloscope, and the Siglent one up here. I have the output set for 1 kilohertz, 5 volts peak to peak into a high Z load, and I have the inputs to both scopes set at 1 megohm, so that's high impedance. The Tektronix is measuring 4.73 volts amplitude, not 5, and the Siglent is measuring 4.76 volts amplitude, not 5. So the output amplitude is low. Now, just to make sure that we're measuring the right thing, I have my PD-VS2 Mini here set for 2.5 volts. And you can see when I run it into my Keithley meter down here, I'm getting 2.5 volts out of it. And in fact, I know this is good to within 10 microvolts. I've measured it on fully calibrated instruments, so I trust it. So let's take instead of looking at the output of the generators, let's go into the PD-VS2 Mini and take some measurements. So right now I'm measuring 2.478 volts on the Tektronix. That's about 20 millivolts off. And they're 8-bit oscilloscopes, so on this scale, it's really 30 millivolts is 1 bit. So that is about as good as you can get. And you can see up here, about the same on the Siglent. So I'm within 1 bit accuracy of the 2.5 volts. So let's flip this around and look at minus 2.5 volts. Okay, so now on the Tektronix, I'm measuring minus 2.48, and the Siglent is minus 2.52. So it's each one is about 20 millivolts off the 2.5. And again, it's 30 millivolts is 1 bit. And even though I have these in high resolution mode, that adds bits to the relative accuracy, but not the absolute accuracy of the oscilloscopes. So now let's check the output of the channel 1 here again. Clear sweeps. Okay, so again, I'm getting 4 point, why don't I turn it on? Yeah, 4.73 volts amplitude on the Tektronix and 4.77 on the Siglent. That's well below the 5 it should be putting out. And you can see here, that's channel 1. Let's move over to channel 2. Same thing. I'm getting 4. Let's restart the measurements on each. So I'm getting here 4.75 volts amplitude on the Tektronix and 4.76 on the Siglent. That's pretty far off. That's like 6-7% off from the 5 volts peak to peak it should be. That's not very good for a $20,000 instrument. Now, just for comparison, let's look at my Siglent SDG7102A. Again, it's set for 1 kilohertz, 5 volts peak to peak on both outputs. So we'll clear the sweeps here. So you can see on this one, I'm getting 4.92 on the Tektronix and 5 volts amplitude on the Siglent, and both are within the accuracy you would expect. So the output amplitude is right on this. Looking on the Tektronix, you can see it's got a little bit of negative offset in the output, and I know it has that. And we'll look at the other scale as well. And here we go, 4.96 on the Tektronix, 5 volts on the Siglent from this generator. So clearly this one has an amplitude problem. Now, this has a self-calibration mode. So if we go here we have nothing connected to it. So if we go to utility mode here and test in cal, it will do a self-calibration. And so we will do that right now, perform the self-calibration. So we're going to let it do its own self-calibration. Okay, it just finished self-calibration. So let's go back to the waveform mode and put it in square wave. Again, 5 volts, peak to peak, 1 kilohertz. And let's do that for both settings, both channels. So they're both set to 5 volts, peak to peak, 1 kilohertz. Now let's hook up the oscilloscopes and see what we get. First channel 1, and I'll reset the measurements. So now instead of getting 5 volts of amplitude, I'm getting 5.6 volts of amplitude. So instead of being 6% under, That's like it's 40% over or 20% over. It's way too high. And you can see that getting 5.68 on the Siglent and 5.64 on the Tektronix. Let's look at channel 2. Reset it. The measurements. Again, 5.62 on the Tektronix and 5.68 on the Siglent. And it's supposed to be 5 volts. That's very bad. So let's go back here. Go back to the utility and let's recall the factory settings. Okay. So it's still outputting, but let's now turn the output off and on. And now we're back to the low setting we got before. So the calibration that came from the factory is wrong, and the self-calibration just makes this thing worse. So here's an example of the fastest triangle wave that this generator will put out. It will put out triangle waves up to 10 megahertz, 12 volts peak to peak. And you can see that they look good on the scope. So that's pretty impressive. Again, the amplitude's a little low, but that's the amplitude problem with everything with this generator, is that the amplitudes are not right. I have the output of channel 1 set for a 12 volt peak to peak triangle wave. The amplitude is a touch low, as it seems to be with all waveforms out of this generator. But let's see the DC offset value. So you can see up here on the generator, I'm varying the DC offset. So I can shift this up and down. Oh, there's the bad control. So now I'm at the maximum. So I can shift 6 volts up with 12 volts peak to peak into 50 ohms, which means the top of this is 18 volts into 50 ohms. I can go back the other way. So that's minus 18 volts. So open circuit, that's 36 volts. Okay. So the fact that I can do 18 volts means I have to be careful about the signals I put into this oscilloscope. I could actually blow up the 50 ohm terminations built into the oscilloscope if I ran straight in. That's why I'm using these 20 dB attenuators on the input to dissipate the power and attenuate it so I don't hurt the front end of my oscilloscope. So here I have the triangle wave at 10 kilohertz, and you can see it's got the amplitude issue that we saw before with the square wave. Let's try the sine wave. Again, same thing. It's supposed to be 12 volts peak to peak. It's running a bit low. Let's try a DC level just for the hell of it. Let's try 4 volts. Oh, helps if I use the right keyboard. It's a bit low too, but not bad. It's close. So let's go back to the triangle wave just to see what happens. One of the production issues I've seen with this unit is that the rotary encoder on this unit is defective, and that's not very good for a $20,000 instrument, and especially a demo unit you're sending for people to try out. Now, if you notice here, I put a piece of black electrical tape on the encoder, and I've marked a couple of other pieces of black electrical tape on the front. And so you can see about 2/5 of the rotary encoder range, this range in here, is where it seems to be defective. Now, I'll come over here to the good range, and you notice as I rotate the encoder, it selects between the various spots on the screen. But now when I come in here, it either doesn't work or jumps in the wrong direction. So I mean, I have 3 other pieces of Siglent gear I've had for a couple years now, and I've been very happy with them, and there's no problem with the rotary encoders. However, this one is defective. I don't know if they have some sort of supplier issue on rotary encoders, but this just is not good. Let's see what other waveforms we can do. Can we do a triangle wave? Yes, we can do a triangle wave in differential mode. That's cool. Can we go to 10 megahertz? Yes, we can. Can we go to 2 volts peak to peak? 2 volts. Enter, yes, we can. Can we get any higher? No. Okay. Let's see. Sine wave. Can we go 500 megahertz on the sine wave? Ah, yes, we can. But let's see now if we can see that on the scope. There. Yes, we can see that. Okay. Let's see, what can we do with the square wave? Square wave, we're limited to 240 megahertz. And 2 volts peak, again 2 volts peak to peak. Okay, let's go back to sine wave. Let's go 800 megahertz. So this is pretty cool. I like it. So now we're looking at the differential output of a 50% duty cycle pulse waveform. I currently have it set for 2 volts peak to peak, which is the maximum amplitude it will put out in the differential mode. So if you look at the scope here, the yellow trace or channel 3 is the positive output. The blue trace or channel 2 is the negative output, and the purple trace is the difference of channel 1 minus channel 2, or the differential output. And they're all set for half a volt per division. So let's see what happens when I play with some of these things. Let's first try the offset. So offset moves the differential signal up and down. It changes the negative output negative and the positive output positive. So it's essentially, we're shifting the whole waveform up and down. Okay. Now let's look at the common mode output. So the common mode output shifts the plus and minus waveforms up and down together, but does not change the output until it gets to here. So we've hit a hard rail here. It will not swing past -1 on either one. So if I try and push it farther, it pushes that waveform down in value, and you can see it's changed this. So let's go back to 2, and let's come back to this one and go positive now. So there seems to be a kind of a hard rail they're hitting at 0.7 volts, maybe positive and negative, and that's limiting how much the differential output can swing. So you can't get a whole lot of common mode range with a big swing on differential swing. However, if you were really doing this, let's say for high-speed logic, let's say some sort of custom high-speed logic, you'd probably only be swinging about 0.2 volts there, max, maybe even less. So let's see what happens now. Channel 2, channel 3. Okay. So now we can come down here. Now let's see if we can change this a volt. Nope. Well, that's because it swung off the screen. That's not the signal generator, that's pilot error. No, a volt up and nothing. Volt down, nothing. So we can't get that much range. How much range can we? About 0.6 up. 0.6 down. So not a whole lot of common mode range even for a reduced swing. Let's look at the offset with this reduced swing. That, okay, so we can get plus or minus a volt offset for the two waveforms, but not a whole lot of common mode difference. That's kind of interesting. Differential mode with the positive going into channel 1, the negative going into channel 2, and math being channel 1 minus channel 2, and that's what the measurements are being done on. I have the rising and falling edges set for 500 nanoseconds. It's measuring 550, but again, that's close enough to the limit of the scope. It probably is 500 nanoseconds in this mode. So this is the maximum swing you can get out of it in the differential mode, which is too bad. It would be nice to see something else, but unfortunately the negative output is limited to, in each one, is limited to plus or minus half a volt or 1 volt. Okay. Here I'm still in differential mode, and I'm at a 5 megahertz repetition rate. Channel 1 is the positive output, channel 2 is the negative output, and then the sum is the purple trace. Now let's see what happens here. I have a common mode voltage I can change. So here I can shift the channel 1 and channel 2 up and down together with the common mode waveform, and the sum and the difference remains the same, which is correct. Now let's hear if I have a offset. Now I can move this. So if I move this to 0.1 volts, I think it moves each one up 50 millivolts and one down 50 millivolts. So you can see here that it's moving them in relationship to each other, and the sum is moving as well. So I can move that down. So this is kind of cool. It's just you can't really do it at 2 volts peak to peak. You can do it at reduced swings. But typically when you're doing this for logic levels, your swings are on the order of a couple hundred millivolts, so this is probably fine. It would just be nice if it was bigger. We've reached the end of part 1. If you liked it, please give it a thumbs up. Please consider subscribing if you want to be notified of parts 2 and 3. And thank you for watching.